Continuing with our get problems for multiple diode, here is another problem. For the circuit with ideal diodes shown in the figure, the shape of the output for the given sine wave input will be, and there are four options which are provided, which shows the output waveform, where the input waveform is a sinusoidal waveform, and this is the circuit that is shown here. So it comprises of a diode D1, and then there is another diode D2, and there is this load resistance RL across which the output waveform should be identified. So consider the fact that this is an ideal diode, and we know that with ideal diode, when it is in conducting mode or when it is in forward biased condition, then the diode should be substituted by a short circuit, whereas if it is in reverse bias condition or it is in non-conduction mode, then you should replace it with an open circuit. So here is the way to work out this problem. Now during the positive half cycle, we can find that the flow of direction of the current will be like so. If you can follow the pointer over here, so this is the flow of direction of current when the input is at its positive half cycle, and therefore we find that the direction of flow of current is from anode to cathode for diode D1 as also from anode to cathode for diode D2, and therefore you can substitute these two diodes with their short circuit equivalents. And so what we can do next is we can apply KVL and formulate the fact that if I start from this node, then minus of V in minus of V out should equal to 0. Or we can find that V out is in opposite polarity to that of V in. So V out is equal to negative of V in. And this simply implies that if the input was a positive going sinusoid, then the output will be a negative going sinusoid. So note the fact that for the positive half cycle, output is exact replica of the input, but it is in phase reversal. Whereas for the negative half cycle of the input waveform, so we are considering the waveform from t by 2 to t seconds for the input waveform, and we find that the current through the diode would have been in opposite direction. That means it would have tried to flow from cathode to anode, and this is obviously not allowed because diodes are unidirectional elements. They will only allow current to flow from anode to cathode and will block current if we try to make it flow from cathode to anode. So diode D1 is in its blocking phase, as also diode D2 is also in its blocking mode. So both these diodes should be substituted by their open circuit equivalent, and therefore the current that flows through this loop is equal to 0 because there is no path for conduction of current. And the output voltage, if we write it as current times some resistance RL, then the current is equal to 0 amperes, and therefore the output voltage turns out to be 0 volt. So for this half of the input waveform, the negative half cycle, we find that the output voltage is equal to 0. And therefore, if we look at the final output, it will be the addition of these two signals. This is from 0 to t by 2 seconds, and the other one is from t by 2 to t seconds, and we find that during the positive half cycle of the input waveform, the output goes negative, whereas for the negative half cycle of the input waveform, the output stays at 0 volt. So this is a half wave rectifier, and the output will be the average DC value should come out to be in negation, and as per our options provided, option number C is the correct answer. So maybe as a homework problem, you can go one step ahead and try to calculate what should be the average value for this output waveform, given that the circuit that was given to us was like so. And as an extension, what you can also do is you can, instead of considering them as ideal diodes, treat them as diodes where the forward biased voltage drop should be 0.7 volt, and the reverse in reverse bias condition treat it as an open circuit, and then try to find out what should be the average value, what should be the waveform at the output, and so on.